half of the battle in life is showing up. I recently had to part ways with a teaching assistant who had been studying with me for 1.5 years, who just refused to go into the lab of research. Now he doesn't have a job. So, if you're the type of person who's like, well, I have these classes, and I went through my 8 years of school, and I missed 2 classes because of pretty big sickness, and that's it, right? I took that really seriously, and I can tell you it pays off even on days when you think like the lecture material is kind of dry and just the 4 hours of sleep, and sometimes it matters. That pays off later in life. A lot of the people who we give you a little bit of life perspective. A lot of the people who are lazy now and taking joke classes now are the same people who are going to be in their mid to late 30s whining about why they don't have money and they want to vote for Bernie Sanders and all this stuff. Right? So, meanwhile, I busted my butt when I was your age, and now I'm gainfully employed and I'm happy and trying to make a difference in people's lives. So, since you are the ones who decided to show up, I will reward you. I will count this as a TGO assignment. So thank you for putting it. My philosophy, it's the same thing with, like, I had one group in my office hours last night, right? And I saw them, the purpose of the report is not just to prove that you can write and know English, but it's to demonstrate that you have some sort of knowledge. The whole point of a course is to try to figure out, for me to put knowledge in your head and try to extract as much out as possible. So even if the code isn't quite working, if you document, we troubleshooted this, we did this, you do it thoroughly, I can find, hey, maybe their code doesn't reflect that they know that, but their documentation does. So everything with what I'm doing, I want to document effort, I want to document hard work. There are students who are working really hard but struggled on exam 1, but then quiz 2, you can start seeing the improvement. They're starting to get it. Those are the kinds of things. I'm going to reward effort every time. I think one student came up to me, and I also rewarded integrity. Student came in, he was late, 15 minutes late, I overslept. Sorry, no excuse, it's on me. All right, that's cool. Tell the truth. Integrity is a big part of being an engineer, right? Would you like the people who built the other 2 floors of this building, would you like them to tell the truth, or would you like them to have been liars? So that's my attitude on these kinds of things. So that's why I did that. So anyway, I consider this to be a really important lecture because everything before and after all kind of ties into this understanding of the data path. Today you will have built an entire computer. And by the end of project 3, you'll have done what's going to be, I think it's 14 or 15, this whole topical guide objective. So this was the data memory stage where we have our registers here. We get our 2 outputs. We always get 2 outputs from the registers, no matter what. But then we have the sign extended value, which comes from where? What 16 bits?
Is it a 3216 multiplexer?
No, that's over here. Yeah. What are the 16 bits? Where does this come from? If it's going into an immediate, where is it coming from? No, that isn't coming from. This is going to be the alien. Even simpler. Get rid of everything but the last word you just said. No, that was everything. What was the last word you said? R-type what? No, R-type instruction. It comes from the instruction, right? So we have the previous stage where you have the all of the instruction. 31 to 26 goes to control, right? 25 to 21 goes to read register 1. Read register 2 always gets 20 to 16, and then it's gonna break off, and you have 15 to 11 here in the multiplexer, right? So everything comes out of the register, and then the last 15 bits come and go there. That is, we go to this here, right? So we get this even more so. So this is what I was talking about. We have the instruction comes out, and then we have our 15 bits here that become sign extended and go to this magical place. Well, now this is talking about the magical place I mentioned yesterday. And so now we make a decision. If it's an R type, it goes through here like so, because the ALU source in your 64 to 32 mux has 0. If it's 1, that means it's an I type, and it selects this one. So it's called ALU source, as we mentioned yesterday. Now, the other thing is we use this to calculate our branch address. So we have our shift left logical. So we multiply by 4. Remember, this is PC plus 4, right? So that means we've already added 1. So now that you guys are starting to work on the section 6 portion, you understand that you have to get 8 bits, 8 bits, 8 bits, 8 bits, concatenate it to a 132-bit instruction, right? So then you add PC plus 4, that comes out of the adder. So every single time we add 1 instruction automatically, because in a normal instruction, you're just going to the next one. So then you account for that here. You add the next instruction plus the number of instructions that you want to branch. Here's one choice. And then this goes around here, like so. Just the normal next instruction. If you don't want to branch, then this is going to go through. If you do want to branch, but the comparison isn't met, it's going to be 0. But if you do have a 0 bit here and a branch, then it'll allow the instruction that you want to branch to come through there. Likewise, we've calculated, so if this were doing a load word or a store word here, we've calculated our base plus our offset. And that calculates our base address that we're pointing to. And then, read data 2, if you recall from store word instruction, the format is store word. So if we had S2, say we said 8 S1. Remember this? So here's what's actually happening. This is what's physically going on. You have read data 1 is S1. 8 is an immediate value, so it's coming from 16. It's been side extended to 32. ALU source is going to be 1, and it's added. And we have our base pointer to the address in data memory. Now, what about S2? We're storing it. We're storing the value of S2 to this location in data memory. We get that from the registers from read data 2. That's where I mentioned last class we have this fan out. So it circumvents the ALU, goes all the way through here, and goes to this write data. So that is for a store word instruction. So if there's a store word instruction, that means memwrite is going to be 1 and memread is going to be 0. Now for a load word instruction, here's what's happening. S1, 8, S2, right? So read data 1, sign extended value, ALU source is 1, and it comes out here, right? To calculate this. So now what's actually going to happen is we have this read data output. This value is going to be output, and we're going to go back and we're going to have this mem to reg where it's going to put these two values in. It's either going to put the value calculated from the ALU. Here we have 0, and it's going to go back to the registers. And at the registers, we have reg write, and the value chosen from reg destination is going to be S1. So when we get to the full data path, I'll go over that again. So programming assignment 7.4, which was we ended yesterday, for data memory storage. So for jump 7.11 and 7.12, jump is a control signal to determine if the instruction is a jump or not. 1 if it's a jump, 0 if it isn't. Seems pretty straightforward. So then again, we have that ALU output and the read data output that we use to compare the branch and the PC plus 4. We're going to be using that plus the result of our PC relative addressing. Remember, we take 26 to 0. We shift left by 2 to get 28 bits. And then we concatenate the 4 most significant bits from PC plus 4 to that. We take that result, put in a multiplexer with the branch and PC plus 4 that we had from the previous diagram. And we're going to use this jump multiplexer to do that. And then mem to reg, which I just referred to. On an exam, it's perfectly acceptable to go MTR. Most of you will do that because it saves you time. Determines whether the result from the ALU or the read data from data memory is written to the determined register. So since it's called mem to reg, the way it's defined is if it's coming out of data memory, then it's 1. Since it's memory to register, if true. If it's not memory to register, then it's going to be the output from the arithmetic logic unit. which then goes back to the register. Is that okay? So I'm going to go up to 7.12, but 7.13 is going to be this truth table here. I'm going to recreate it. So basically, you have instruction, you have R type, load word, store word, and it's called branch equivalent, right? So first, we're going to do register destination. So register destination means I want to select which register is going to select. Remember that in the instruction decode stage, we had 20 to 16 to 15 to 11 to determine our destination register. So in order to do that, if it's an R-type instruction, we want to select 1. Now, why would we want to select 1? Without trying to squeeze your eyes and look at the table, anyone know why? If you recall from the instruction decode stage we went over last class, any ideas? If I'm making a decision between an R-type and an I-type instruction. Yes, Tony. All right. So, any ideas? Joseph, it's on the tip of your tongue. I can see it. But you're picturing the instruction formats in your head. I can see it. And you have to make a decision between what?
Between which instruction you want.
Correct. And but more specifically, not the opcode, but you're on the right path. So the opcode always goes to the controller, not the function. You guys are on the right path. It's
one of those.
It's anything but those. It's like you're hitting everywhere. You're getting closer. First it was data path. Now it's part of the instruction. But I'm deciding what. If I'm deciding hidden the name. Remember, the names are chosen to be intuitive. Register destination. So what am I choosing between? RT and RD. Very good. That's exactly what I want. So if it's 20 to 16, what is it? RT. Yes. So we said RT is and if it's RT for our destination register, what type of instruction is it? I type. So that means load word, I want to write to the register. So if it's an I type, I want it to be 0. If it's an R type, I want it to be 1. So for store word, am I writing to the register? I see a lot of sheds shaking no. Somebody be confident and say it. Good. Okay. So if I'm not writing to the register, what values do you think I want there? 0? So in that case, I would be writing RT if it's 0. So what do you think the value should be? Do I even care? No. So if I don't care, what should I put? Don't care. And so what allows me to not care? What do you think allows me to not care? What was the control signal that goes into the registers? That allows me to determine whether or not I want to write. What's the name of the control signal? Reg write. So that allows us to do this. Reg write. So I want to write, I do for R type, I do for load word, say 0 and 0. So if you recall, we go all the way back to SRAM, where if we set the write value to 0, that means it's never going to update. So by updating this reg write value, we can send all the data we want to it, but if it's not going to allow us to write, it doesn't matter. You see, this is a good combining concepts portion. Dual read, single write. I don't want to write. So reg write, that's how it works there. So again, if you recall this mem to register that we just went over, I'll do that since we just went over it. If I want to write from memory, which one am I using? Memory to register. Right, memory to register. So I'm reading from data memory, writing to the register. Load. No, that's load word, correct. So when do I want it to be 1? Load word.
When you want to be reading something.
Well, you want to read from data memory and write to the register. So memory to register. So if I want to update the registers, but I'm doing an R-type instruction, that means I want the other value. Because these are all controlling multiplexers, this truth table. So that means I want a 0 here. And again, since I'm not writing to the registers, these are both don't cares. So if you have ALU source, I'll do ALUS for the short here, but ALU source, that's this one. So for zeros, I want R type. For immediate values, load word and store word, I want 1. Because that's the one where we're taking the sign extended 16-bit value from the instruction, becomes 32 bits, and we take that and that multiplexer that compares them, that's the immediate value. Now, what value do you think I want here without having looked at the solution? I know putting that over just makes it on my end. What solution do you think it should be?
0.
Why? I understand you can read 0. Hope you figured that one out in kindergarten. But why should it be? Why is it not a 1? What did I just say 1 is? Yeah, doing the sign extended value. So what am I doing for a branch? Think back to the branch instruction, right?
Are you jumping just to it?
No, branch is not branch is branch. So I remember this. I have S0, S1, and then I have like 6. So 6 is the number of instructions I want to branch past. So how many registers do I have in that instruction that I just wrote up? 2. So where am I getting the second register value from? Okay, so you're getting S0 is coming from read reg 1. And where's the other S1 coming from? Sorry, read data 1. Where's the other one coming from? RD2, read data 2, right? So it's coming from a register. So if it's coming from an immediate value, it's going to be 1. If it's coming from a register like R-type, it's a 0. So the same thing with branch, it's reading from a register, so it's going to be a 0. Does that make sense? Next thing, the next topical guide objective is the full data path. We're going to be going over all this again. So we've done mem reg write. We've done reg write. ALU source. We've done ALU source. We've done it. Mem read. What instruction do you think I want to do for mem read? I'm reading from data memory. Load word. Correct. So we'll just mem read 0, 1, and everything else is 0 because I don't want to read it except for that. Mem write. Which instruction do you think that is? Store word. So that'd be 0, 0, 1, 0. Let me erase this. And so a lot of this becomes, so branch, which one? Yep, just branch, right? Now, these are the two that I've alluded to in the past, but now we're going to go over again. So ALU op 1 and ALU op 0, where do those go? Yeah, so ALU opcode. Yeah. So there's it's a 2-bit control signal. I've told you where it goes in section 3. I've told you where it goes in section 5, and I told you where it goes yesterday. Joseph, where does it go?
Where does it go?
Yeah, where
does the sign extension?
Yeah, it goes to the same place as the sign.
That goes where the sign extension.
What's that thing called?
Concatenation.
Well, no, not concatenation. So I have ALU opcode, and I have my function, and they go into what? Which determines the 4-bit output that goes to the ALU.
The decoder.
ALU, let's get ALU controller, but you guys are on the right path. So it goes to the ALU control. So for the time being, what you need to know is for all R-type instructions, remember how all R-type instructions have the same opcode? So all R-type instructions, ALU op is 1, and ALU op 0 is 0. And for all branch instructions, it's 0 and 1. So anything coming from those. And then everything else, it just goes 0 and 0. Because what am I actually doing in load word and store word? What am I actually doing with the arithmetic logic unit? Transferring data. But what am I doing specifically with the ALU during a load word instruction or a store word instruction? I'm transferring data from the, you are correct, I'm transferring registers to data memory is store word and data memory to registers is load word. But how do I know which place in data memory I need? Not a multiplexer. What am I specifically doing with the ALU? To calculate the base address of the array. What's the function that I'm doing with the ALU? Adding. Yes. Yep. So it doesn't matter because we're always going to be adding. So they're both going to be 0 and 0. So let me scroll up. So for those of you watching again on the this is the full truth table that you all have just reverse engineered. And then this year, you're going to be designing this. So I want to go over all this. If you, I'm going to give you a hint here. So you see all these adders, I mean, not the adders, AND gates. If you go to AND, so you have a 6-bit input from your opcode, op5 through op0. And you notice how op5, all of these is the same. op5, op4, op3, op2, op1, op0. And you have your inputs here. So this is something that I noticed when I was taking this course back in years ago. And but what is the if you remember from the MIP screen sheet, what's the hex value for a for an R-type instruction in the opcode?
Hex 20?
No, we mean what's the opcode value? Look at any R-type instruction. Now there's opcode / function. So you were right, you asked for the function. It is zeros, right? So it's 0, 0, so it's 6 bits. So if you're taking the inputs into an AND gate and you want to negate everything, that's 0, 0 hex, which means it's 0, 0, 0, 0, 0, 0, 0. 1, 2, 3, 4, 5, 6. Now, if you put negations at the inputs to your 6-bit NAND gate, those are bubbles, right? Bubble, 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 bubble. Now look up add I instructions, an I-type instruction. What is my hex value for that, for the opcode? 8 hex, right? I can tell you it's 8 hex because I can see here 0, 0, and then 8. Well, there's all of these have bubbles because they're all being inverted. If it's not being inverted, it's just a straight line. So it actually happens to match. Yeah. So load word I can tell you is 2, 3 hex. This matches bubble, bubble, bubble. So that's a little class hack that I figured out back in the day. And then so load word, I'll zoom in on all these. Load word is 2, 3 hex. Store word, 8 plus 3, 9, AB. So it should be 2B hex, right? BAQ is going to be 0, 4. So it's just going to say 4 hex, right? Is that what branch equivalent says, Saber? Yep. And then I've included branch not equivalent because you'll need both of these for your final project. Branch not equivalent is going to be 5 hex.
0, 0, and 5. And then last but certainly not least, jump is 2 hex. So the rest of this is just logic. So for register destination, we're just translating this table here. Register destination is 1 or 0. So R type, it's only going to be 1 when it comes out of R type. You see? So all these values over here are just the case. These are all just OR gates determining when I want a value to be 1. So ALU source, 1, 1. So I have add I is an I-type instruction. I want that. Additionally, load word and store word, as you can see here, load word and store word all go into these two OR gates, right? And so that's ALU source, add I, load word, store word. Mem to reg, I only want it to be 1 here. So mem to reg, I only want it to be 1 when it's a load word. So you see load word here, mem to reg, load word. Scroll up a little more. Reg write, I want to write to the registers for R-type instructions, a load word instruction, and add I instruction. Because I'm taking value from a register, I'm adding the immediate value, and I'm storing it back in the register, correct? So register write from R-type here, load word here, add I here. So as I'm sure you probably see, I'm making this a C programming assignment. For those of you who came into my office hours yesterday, which felt like it never ended, but which is a good thing. I like it when students come by often. But you see, this is how I told you all about drawing out your designs before you code. This is an example. This is what I did for when I designed this in C. You have your AND gates, which you can put together. You can design a 6-bit AND gate by using 5 AND gates, right? You can go op5, op4, op3, op2, op1, op0, and there's your output. And you just have to choose which ones to negate. So all of these are negated for our R-type instruction, right? So now you can just bool, you can call it 0 or whatever, or L0, or then you define all of those, and then your function output. So what I would do is I would just define a 6-input NAND AND gate using your 2-input AND gates, and then use your knots to correlate to the zeros in your hex code to the inputs. And then once you have these intermediate values, you can just say, you could say bool R-type, bool add I, bool load word, bool store word, bool equivalent, jump. So over here, you can create a function. When you create your function controller, you can have a pointer to regdest, bool star regdest, right? And you say star regdest equals R-type. So you want to pass the pointer by reference to the function call, so that we're talking about the function that we've called. So there you go. So then here you can say star LU source equals or, and then your 2 inputs are add I and load word, and then you have an intermediate value here. And that could be your first input to a second OR gate, which then becomes store word. You see how I'm doing that and taking advantage of drawing this out to write the code out. And so if you just write the name, so if I just called this, R-type, RTY, and add I, bool add I, and you write these out like this, take a picture, put that in your report, boom, points. My goal is to reward effort. And I think one group had a beautiful ALU design in their report. I was looking at it, I was like, I want this to be done for everyone. In fact, actually I can't use that as a report because I'm basically giving everybody the solution to project 1. But
I'll probably put up the picture and say, here's what I want you to do. Don't use this exact photo. That's plagiarism. But you see, you see how you can use this as a way to design? And you're showing me, if I just get a bunch of gobbledygook code that doesn't work, I'm like, okay, well, they don't know what they're doing. But if I see this, and I can go through and look at your code, and let's say your code doesn't compile. And I go, well, what happened? If it hangs up, and let's say you made a mistake. Let's say instead of saying bool load word here, let's say you said bool star load word. So you just created a pointer to a bool, and then you did load word equal, you did star BQ equals star load word, right? So that's just a minor pointer error. What you've done is you created a pointer, but you didn't assign the actual value to it, and the value to that location. So I'm passing the location to a dereferenced pointer, and that's where you get hung up. And I can go, okay, well, I can just get rid of this and get rid of that, and their code works. So instead of taking 10 points, that's a half point. You see how laying it out and doing it like this significantly, because now you've demonstrated, I know I have a knowledge, I just made one minor coding mistake. So that's, and the other thing that I mentioned to one group in particular, when you apply for jobs once you graduate, there are a number of websites that will ask you for code samples. So if you have well-commented code samples and a nice report that describes what it does and it actually simulates a MIPS data path, that'll put you ahead of somebody who just has a resume. So my goal in doing all this is to try to get you guys paid after you graduate, right? Do all this effort, you come into class, you do all the TGOs, and then you live nicely and you don't have to beg for money. So that's the combinational logic. And so the next portion, this next truth table that we're going to go over before you go through the final data path, this whole combinational logic for the ALU controller. So I kind of alluded to part of it, and I said, remember, there's going to have the 16-to-1 mux, and then you just have certain ones. So what you're going to do is you go and or, set less than nor. You're going to have an add I value that you're going to calculate. Load word, store word, all of these are add, branch equivalent, branch not equal, and jump. So now you're going to use things into the ALU, which you then can use. You've already got it. All you have to do is just take the result, put in the line of code that calculates it, have it go into your for loop, put in that one spot where you're calculating output of I in your for loop, just put it there, and you're done. So you've done the heavy lifting already. So now it's just fine tweaking it. So desired function add, remember I said 1 and 0? All of these are R-type instructions, so they're all 1 and 0, right? So now we're add I, load word stored, branch equivalent. And so add I, load word store word, they're all zeros. Because they're I types, but they're just doing addition. Branch equivalent, 0 and 1. Branch not equal, 0 and 1. And then jump. I put this here, even it does produce an ALU control signal, but it's not going to do anything. So it doesn't matter what we have on the output of the ALU, because the whole point of the jump is you just get your 26, add to, concatenate, and then go to that instruction. So you don't want to have anything else done. You do. So jump, that's why reg write's going to be 0, memory is going to be 0, mem write's going to be 0, because you don't want anything else to happen in the data path. It's going to do all these goofy calculations, but you don't want any of your values to update. So function. Then you go through, it's going to be 2 0 hex for add, 2 5 hex for or, 2 4 hex for and, sub is 2 2 hex. So I'm just taking the function and putting the hex equivalent to 2A hex, and then 2 7 hex for nor. And then, so this is just the binary and hexadecimal versions. You write these out. So the whole goal is you're going to get in the function. Your inputs to your ALU controls, you set programming 7.6. Your inputs are your 6-bit function. So you have a bool array, bool star input. You have a bool for ALU op 1, bool for ALU op 0. Some people will create a bool star for a 2-bit array.
You may do either one. And then you just do logic to get these outputs. You see how for 20 hex 00 your output is 0001. So this 4-bit goes to your ALU, and where does it what's the value of this 4-bit ALU control? What does that ultimately control? What portion of your ALU does it control? Multiplexer, very good. Your 16-to-1 mux. So you tie this output to the input of your 16-to-1 mux. Done. And so 0001 is what happens when you get 10 and 25 hex. All zeros is for AND, as you recall. This is kind of just this is somewhere in, I think it's 3.14 on steroids. So this is the whole thing. This is the code that I give you to do for your final project will use these instructions and these instructions only. So you're going to do a slightly truncated version of the data path, but it will work. Subtraction 10 to 2 hex gives you 0110. Set less than 10 to a hex gives you 0001 on that output. NOR 10 to 7 hex gives you 1100. The rest of these, you notice how load word and store word and add I. You know what do these functions actually do in the ALU? Add I, load word, and store word. I actually just asked this question a moment ago, so hopefully you guys know what it does. What does the arithmetic logic unit do for load word? Add. Say versus add last time. So what does that mean my output for my ALU control should be? Yep. And the reason why, why is it that? And it's add. That's what I wanted to say. So it's add, and look what it does. They're the same. So if I get 00 on the output, I want the same values. But they're I-type instructions, so the control of the opcode is going to be different. So you're going to hard code that in there. And then 0101 is going to give you, for branch equivalent, give you 1000, 1001 for branch not equal. And so for remember you have your comparator. And so you have, if it's 1, that means they're the same. If it's 0, if it's not, so that's when you put in branch equals. So the simple way is just to invert the result and put it in branch not equal. And then jump, well, it needs some sort of value. Technically, this could all be don't cares too, but you're going to need some sort of value sent there. All right, so does that table make sense now? I'll ask again. Hopefully everybody gets it this time. What does the ALU do for load word and store word instructions? Adds. Good. All right, you guys are awake. So 7.6. And so this is the omega diagram. This is your full MIPS data path. Everything we've been doing up to this point builds to this. Here's how it starts. Your program counter goes out here, goes up to, you have an adder that says 4. So you have a calculated PC plus 4, right? This goes to instruction memory. This says read address. And then it calculates the output and gives you a 32-bit value there, right? The value, we have our instruction. For instruction decode, there we go. 31 to 26 goes to our controller. Now, if you look in the textbook, you're going to see it has a bunch of control signals coming out. I'm not going to require you to do that in the exam because it can get messy. When you see here that I have the control signals just drawn really close to where they're used. That should say mem read and mem write. So here's what's going on here. You have 31 to 26 goes here. 25 to 0 is the 26 least significant bits. So this is our PC relative, shift left logical. Now we have 28 bits. We have PC plus 4 comes out here. We do our, here Joseph, try saying it again. What's the word? Concatenate, right? This says 31 to 28 here. That means it's their most, PC plus 4 are most significant bits. And now we have our 32-bit output. So then we have PC plus 4. Now, before we deal with anything else, this goes here. This is our 16 to 0, right? And 15 to 0. We sign extend it to 32 bits. And it comes up here. We shift left 2, so then we have the number of instructions that we've branched. We've add them. And this goes into branch. We have jump here. And then that is how we calculate our next instruction. Okay, before I deal with any of this up, does what I just said make sense? Does anybody have any questions about it? All right, so instruction decode stage. 31 to 26 goes to our controller. That is our 6-bit input into the control that I showed you for those 2 TGOs. And now 25 to 21 comes here for read reg 1. It's always the case. Read register 2 always gets 20 to 16. So if I wanted to zoom in a little here, you can see this is 25, 31 to 26, 25 to 21, 20 to 16. Now here's where we make our decision. (15 to 11) is here. So this is our R-type instruction. That's an I-type instruction. And that is decided with register destination. Okay. And then this is going to come from mem to reg. So we'll describe that in a bit. So this portion here is our 16 least significant bits. 10 to 6 is, what is this? What is 10 to 6 in an R-type instruction? Shift amount, right? And that is going to go directly to your ALU, which you're working on how to take that input and put it into the result there. So then, sign extended, it becomes 32 bits. We take 5 to 0, so in an R-type instruction, what is this called? Function. Right? And that goes to our ALU control. What's the other input to the ALU control? Just from the previous TGO? I have the function and what else, which is going to be down here. I'll give you a hint. No.
ALU grade 1.
Yep, ALU op 1 and ALU op 0. So those are your 2 inputs. So for the rest of the instruction decode stage, we have register write, which controls whether or not we write to the registers. And then we have our write data, which I'll show you later when I go over this portion. So that's where we're at in terms of this portion of the diagram. So the registers, as you guys are working on right now, taking those 5-bit inputs, we do 5 to 32 decoders here, here, and here. We get the values from our array, and we have, since it's dual read, single write, we can actually get both values to the output. We have our read data 1 always goes to the arithmetic logic unit as the first input. The second input, we make a choice. We always get this output from read data 2, but we also get our sign extended immediate value from here. And so we have to make a decision. So this can be a load word instruction, could be a store word instruction, could be immediate. That means ALU source is going to be 1 from our truth table. If it's 0, it's going to be read data 2, so it's an R type. So if it's R type, Is that I type? Is that R type or branch, I should say. So then, again, we get our value here for set less than 2. PC plus 4 comes from here. We add them together. That is our input. Now, the arithmetic logic unit, you can calculate a 0 bit here. And if they're equal and branch, you get the result, and it comes from here. If not, so if branch is 0, that means we're automatically going to get the result of this out. Or if the branch condition is not met, then so this is like, so what I'm describing here is what happens if you have an if instruction and it meets the condition, right? So if A equals B, then I want to do that code inside the loop, inside the branch. This is not going to be, the 0 bit is going to be a 0, which means it's going to go into the AND gate. It's not going to be met, and we're going to just do the next instruction. So this is going back to the section 2, and I talked about procedural code. This is where understanding C to assembly to machine code becomes important. So now this is how we get to that next instruction. This is how branching and jumping occurs. So then we have an AOU result goes here, and branches passed. So if it's an R-type instruction, here's what will happen. And this is kind of where write data and mem to reg comes into play. If it's an R-type instruction, zoom please. There you go. So if it's an R-type instruction, here's what's going to happen. The result's going to come from the ALU. It's going to go past data memory. Mem read is going to be 0. And mem write is going to be 0. So then mem to reg is also going to be 0 because I don't want the data from memory. Is it memory to register? No. So what's going to happen is we're going to come here, then come back around, follow this guy here, and then continue going all the way to write data. At which point register write is going to be 1. So we're going to come back here, and it will update our result to the value indicated by this register. So we use a 5 to 32 decoder. It determines which one it is. And we use this value to update it. So that's how R-type instruction physically works. Load word instruction. Load word takes the value calculated here, correct? And we get this value. And then the result is put here. Memory to reg is going to be 1, so I'm going to want this value. It's going to come back, go around, go around, go around. And then I have some value I want to load into the registers. Register destination is going to be 0 because I want RT from an I-type instruction. And it writes to the register here in that manner. Store word instruction. I get the value here from read reg 1. So if I do store word S1, 8, S2. So S2 is here. 8 comes from here. That's 8. And it calculates the base address of the array for the data memory. S1 comes from here to write data. So S2, S1 goes there, we get those values and put them on the output. Now this is why I don't care, because reg write is going to be 0, so it doesn't matter which one of those two values I use, correct? Because I can go there, hey look, I have this value I want. Hey, I have this value from over here. Can you write it? Reg write goes, no soup for you. Branch. Here's how the full branch works. So here, well, I should have said one other thing for R-type. So R-type, you get these two values here. ALU source is 0. You get this value goes over here. You get 1, 0 for ALU op. Give the result. And then circumvents. And writes here based off of register destination being 1. Jumping. Go over jump one more time, now that we have the full data path. Jump. I calculate that value, PC plus 4, over here. From instruction memory, I'm going to go to the controller. It tells me my jump control, 25 to 0. Shift left 2 gets multiplied by 4. I concatenate the 4 most significant bits, and that's my output here. This is normally PC plus 4. It comes here to jump. Jump is 1 there. Branch is going to be 0 because this will automatically be 0. So that means I get this value, and it automatically tells me where to jump. Reg write is going to be 0, so I don't want to read anything from the registers. You see how I'm going to get, I'm sorry, let me get rid of these 2 lines so I can tell you what's actually physically going on in the rest of the jump instruction. See how the registers are still getting some sort of value? 25, 21 here. So there's an output, value, ALU source, I don't care, so it could be 0. And it does some sort of calculation, right? It's sent to data memory. Mem write says, no, I'm good, no memory write. I'm not going to read. I go here. Let's say mem to reg was 0, so I have this value coming around here. And I come back to the register. Hey, I have something I want to write to you. Mem register write says no. And same thing with branch. Branch is going to be 0, so that allows our jump instruction to do that. Shift left logical. I have value comes out. And we're going to shift left some sort of value, and then RS, plot your MIP screen sheet. You do shift left logical. You look here, you go there, what does it say? It says RT equals RD by shift amount. So here's what's going to happen. This is where understanding this makes sense. I'm going to get some sort of value on the output, RT, right? It goes here. And I get a shift amount. Comes here. Comes on the output. Goes here. Comes around. And is written to by RT, at RT. So RS, I don't care. So when you have your shift left logical, which I told you to do, you're going to take the RT value that comes in from your second ALU, put that on your output. So how's this coming along so far? Okay, it is 10:30. You guys showed up because the next step is what I'm going to ask you on the exam is not, because this is 6.7. What I'll ask you on the exam with regards to that is we're going to go over, I'm going to give you ask for a subset of the data path. So I'm going to say, give me a reduced MIP single cycle data path that does load word and R-type instructions only. So I'm going to briefly show you this. We're going to stop the TGOs at 7.14. Next Tuesday we'll go over that. The assignment is due. That assignment will not be due until next Tuesday. Today's assignment is due next class. Okay, good. But let's kind of do an example, and then I'll dismiss you guys. So we're going to do R-type and load word. So the reason to ask it this way is because I could just ask, give me the full data path, and that rewards people who have photographic memory. Or I could see what you actually understand about the data path. So PC, I need that for every instruction. I need to get to the next instruction, right? So I use this. Am I going to jump in my choices? So I don't have to worry about any of this. This goes away, that goes away, that goes away, that goes away. Am I going to branch in any of my choices? So you don't need this, you don't need that, you don't need that, you don't need that, you don't need that. So that's just, you can just loop it like that. Make sense? Do you need instruction memory? Always, right? You need 31 to 26. Well, make sure you include, if you do not, I'm going to tell you right now, this data path problem is going to be worth 25 points. If you do not include the controller, you will get a -5. Because the controller controls the data path. If you don't include the controller, it won't work. So if you don't include that, that's a big concept issue. So I'm going to emphasize this, and I'll say it over and over again as we get closer to the exam. It's -5. I know it's a little circle that says control, but it's a big deal. As I've gone over, because we had that previous TGO where I showed you all how it works on the inside, it's a big deal. Do I need the input for 25 to 21?
Yes.
Why? Always.
It's all we need.
20 to 16, do I need that?
Yes.
When? If it's R-type, very good. That's the kind of stuff that I want to hear. What about this? Do I need this multiplexer?
No.
Why?
Because it's an R-type, not I-type.
No, but when do I want to write to a register? We have R-type and load word. Store word is doing what? Store word takes a value from a register and writes to data memory. This load word, I'm taking a value from data memory and doing what? Writing to the register. So do I need this or not?
You're writing to a register.
You're writing to a register, but I also have R-type instruction, right? So I'm either going to be writing 20 or 16 for load word, or 15 to 11 for an I-type, which are for R-type. Now, here's the question. Would I need this if it was a store word instruction? If it was R-type and store word, would I need this? No. Why not? Because you're only going to write from R-type. See, that's why I asked the question in this way, because it makes you actually think about each element. So we do need this, we do need this, we do need that, we need register destination. Do I need 15 to 0? Yes. Not always. If it was just R-type, would I need this? I would just need the 5 to 0, right? But I do need this because I need to calculate, I have my base address coming from RD1 and my offset coming here, correct? So I do need this. Now go here, R-type, I need that to make that comparison, and I need LU source. I don't need the rest of this, so I don't need this line, right? Do I need this line here that comes out of RD2, the fan out? Do I need this one? No, why not? We're not writing, we're not going to store. Very good, very good. So no. I do need ALU control. Do need that. Need that guy. Am I doing any shift amount in this? No. Xavier, tell them what type of instruction on our shift left logical is. Look at your MIPS screen sheet. I know you're the. What type of instruction is it? This column. Shift left logical. Column. R. It's an R type instruction. So I need it. So I don't need that. So now, here, I need this for R type instruction. I'm getting a value from load word. And we're coming here. And that comes back in here. So we need register right. Do we need, if it's a load word, what am I doing from data memory? Reading. Very good. So I need mem read. Do I need mem write? No. So leave it off. And I say this, if in doubt, so oftentimes a student will get on the exam, I'll say R type or load word, and they'll go, oh, do I need to include mem write? I don't think I should. And they'll write a little thing like, I left mem write off because we're only reading to the data memory. And I'll go, yeah, that's right. Again, show me what knowledge you have in your head. Okay, so dues through 7.14, that's due next class. Next Tuesday's class will not be due until Tuesday after. You get the idea. Tomorrow, this one is due. So 7.11 through 7.14.